So our next speaker is Sinan Guturk from NYU.
Thank you, Robert. It's okay. It's very special to be giving a talk here, especially since I consider myself very close to Ingrid, and I'm an academic child of hers, and I will be reporting on the work of actually some of her academic grandchildren, so who are so the talk is on the quantization theory for frames and compressive sampling systems. So here are some collaborators on past work. Özgür Yılmaz, another past student of Ingrid, Ryan Saab, an academic grandson of Ingrid, Alex Powell, Mark Lammers, and the most recent work I'll talk about is my student Evan Chu from Courant. So let me just quickly set up the framework here. I'll be talking about some very conventional A to D and D to A setup, where we have a class of signals X that are sampled by some system phi, then quantized, producing Q, coming from some alphabet, m-dimensional, and then reconstructed by some method denoted by delta. So here I'm going to keep it general. The sampling system could be critical sampling, as in Nyquist sampling. It could be redundant, like oversampling, or it could be compressive. So all cases are allowed. Quantization could be memoryless, scalar. It could be feedback. It could be vector. And the reconstruction methods could be linear or nonlinear. So we have a large class of problems here. For instance, we will always assume that a class of signals are given. Otherwise, if you have a single signal, this problem doesn't make sense. Given a class, and let's say a sampling system phi, you may be interested in designing a quantizer and a decoder delta. Or as a second problem, given a signal class, a sampling system, and a reconstruction system, you may wish to design a quantizer Q. Or given the class, the sampling system, and the quantizer, you may wish to find a good reconstruction algorithm. All of these are valid problems and are discussed in various contexts. And the last one is that given a reconstruction method, you may wish to design a sampling method and an associated quantization method. You can actually go on depending on other constraints that your system may have. And always, for quantization, the goal is to keep the distortion as small as possible, and the distortion will be measured as a function of these system parameters, the sampling, quantization, and reconstruction operators over the class. And I'll look at the worst case scenario, so supremum of the reconstruction error. The reconstruction is denoted by x hat. And the performance can be measured with respect to the total number of bits available. So here, we're mapping signals to m-dimensional quantized output. So if you're using b bits per in your alphabet, then it's m times b is your total rate, output rate. So there are always some kind of universal bounds, lower bounds on how well you can do. These are just entropy-based or volumetric bounds. For instance, if you have a set like a cube in k dimensions, if you're using m measurements with b bits per measurement, you will never be able to do better than 2 to the minus b times m over k. Or another example, if you have k-sparse signals in capital N dimensions and bounded by some cube, then this will be multiplied by a constant that is kth root of n choose k, roughly speaking. So these entropy-based bounds may be inaccessible depending on your setup. Your system may have constraints, like I said, your sampling or quantization or reconstruction algorithms. but they serve as a benchmark, and Ron also mentioned Kolmogorov-Witz as benchmark, so this is in the same sense we can compare performance of systems against the entropy. But the key point here that I will emphasize in this talk is that the distortion must, in any system that is sensibly designed, must decrease with what I will call the oversampling or the effective oversampling ratio, m over k. So if you're mapping k-dimensional signals to m-dimensional measurements and then quantizing them, you are oversampling. If you're in that scenario, the reconstruction accuracy must be increasing with m over k. So and the focus of this talk will be mostly on redundant systems. There are frames, so linear measurement systems, but also on compressive sampling. And compressive sampling may seem like the opposite, but as many of you know, if your signals are sufficiently sparse, then these two notions are related. Knowing the sparsity pattern, you're actually oversampling. These are well connected. I will start with frames, and at the very end, I will hopefully get to the results for the compressive sampling, but at least I would like to talk about the frames bit. And frames will be always finite dimensional in this talk. So a finite dimensional frame, so m elements, it just means in our case, it's a spanning set. I will denote the frame vectors E1 through EM. I'll put them in a matrix E as rows, row vectors, and the sampling operator is just the matrix E multiplying your vector X. And by a dual frame, F1 through Fm, I just mean any left inverse F, whose columns are the dual frame vectors. And you can always think of the dual frame giving you a reconstruction operator delta. So now let's just talk about the quantization theory of frames briefly. So we will have an underlying quantization alphabet, script A, and Q is a quantized measurement vector, m-dimensional. So there are two basic formulations for the quantization of frames. The first one is the synthesis formulation. Here you have a given dual frame, F. So you have these vectors F1 through Fm. And the goal is for each signal X in Rk, find a quantized representation Q such that if you use those coefficients, multiplying your frame vectors, you find as good a representation of your k-dimensional vector as you can. So it's similar to the P4 that I described earlier in the general case, but here the measurement and the quantization operators are fused. I'm not necessarily trying to first sample and then quantize separately. You can find them in any way you wish. It's completely free. But this is a kind of a notoriously difficult problem, because what you're looking for is looking at the whole constellation of all sums. Here I denote by S of Fa, all possible quantized sums. And the nature of these sums depend on the arithmetic structure of their frame vectors. Just to give you a visual illustration of this, here are two cases. On the left, you see roots of unity. These are 10th roots of unity. And below that, you see all binary sums of 10th roots of unity, and the associated Voronoi diagram, which gives you the best quantization cells. And on the right, you also have 10 vectors, but they are in two orthogonal directions at dyadic scales, and their binary sums are all distinct and give you a perfect uniform grid having 2 to the 10 elements. And they give you a much finer distribution of points. The reason is that even though you form 2 to the 10 sums in each case, there are lots of incidences for the roots of unity, which give you a worse distribution. So you see that you can get completely different behavior. In fact, for instance, on the left, if you look at the probabilistic distribution, asymptotically it would be Gaussian, and on the right you see uniform distribution on a cube. Now actually, I said this problem is notoriously difficult. If you just simply look at the probabilistic distribution of these points, it's relatively kind of, not relative, but it's better understood. So depending on how kind of arithmetic structures are present in the frame vectors, you can say something about the probability distribution. But the problem we're interested in is actually more delicate than that. We're interested in the geometric distribution, so questions about a local covering radius. So that's a hard problem. And in fact, the synthesis formulation I will not touch today. So I'll talk about instead the analysis formulation. Here, what we have is a given analysis frame E. So that means we have a given linear sampling system. And we have a number of, so we have three cases that I will discuss. So the first one is given a frame E, you would like to design a dual frame F and a quantizer Q that give you a good system. Or you may be given the frame and a possible dual frame, because there could be many, design a good quantizer associated to this system. And thirdly, given a frame E and a quantizer Q, find the best dual frame F. Now, in the first case, I should emphasize that there has to be a connection between the analysis frame and the synthesis frame, meaning that F should be dual to E. If you don't constrain the reconstruction frame to be a dual frame, then you lose one property. First of all, the property you want to have is that if you do not quantize at all, you want to be able to reconstruct perfectly, right? So that's a reasonable assumption. But also, from a quantization point of view, if you don't have any constraint on the reconstruction frame, then the problem doesn't make sense. You can always design a universal reconstruction frame like the one I'm showing you. It's just you take an orthogonal basis and repeat it at dyadic scales. And since from the measurements you can always reconstruct the original vector, that means you can compute the base 2 coefficients of the original vector and put them in front of your frame vectors. And but that reconstruction frame would have nothing to do with the analysis frame. So in a sense, this is saying that we are always considering here reconstruction frames that are dual to the analysis frames. Okay, now having kind of set this, the question is what kind of quantizers to use. And the standard option that anybody would do initially is to use just a scalar quantization for the samples, right? That's a memoryless scalar system. Now this is okay if you are taking as many measurements as your dimensionality, m equals k, and it would be optimal if you have an orthogonal basis. But otherwise, if you're oversampling, this is highly suboptimal. So this is not the way to go. In fact, the decay of the quantization error in the kind of oversampling ratio would be so slow that it wouldn't be worth doing it. So there are kind of relatively well-known alternatives, and they can be all put into the context of noise shaping. So if you are in circuit theory, you would have heard sigma delta modulation, which is a noise shaping A to D conversion method. And here, by noise shaping, I will put that in a more general context. So the main idea is that if you're oversampling, if m is much larger than k, then the reconstruction frame has a large kernel because you're mapping m dimensions down to k. So you have, because there are so many representations for each vector, you could potentially hope to put the quantization error, y minus q, but it's not the reconstruction error. It's the difference between your measurements, y, and what you quantize them to, q. You can try to push it towards this large kernel of the reconstruction operator, right? So in the case of, for instance, conventional A to D, oversampled A to D, this is sigma delta modulation. The reconstruction corresponds to low-pass filtering, and you arrange this quantized output so that this quantization error is a high-pass signal because reconstruction is done by low-pass filtering. You try to kind of separate them. And, so this is typically done by setting up a difference equation. So here's delta stands for the difference operator. You can take it, you can raise it to a power like r, and you set up this difference equation, which automatically would guarantee that the quantization error is a high-pass signal, because when you differentiate a sequence, you make it high-pass. And that will only be true if what you differentiate is constrained. And here U is kind of a state variable. It's an auxiliary kind of sequence that will only be asked to be bounded. So this is the general setup of sigma delta modulation. You may already know, or you may have heard about this from us, or just to give you a visual explanation of what it's doing. Here at the top there's a kind of an audio signal, and a certain segment of 1 second duration is zoomed in the middle graph. And the first is just simple rounding. So it's memoryless scalar quantization. There's no feedback, there's no noise shaping. And the spectrum of the signal is at the bottom in black, and the spectrum of the quantization noise is red. So you see it's uniformly spread in all frequency bands. But noise shaping, if you do sigma delta, first order sigma delta, you don't round samples to the nearest quantization alphabet value. You kind of do this noise shaping. And now the magenta curve and it tells you the spectrum of shows you the spectrum of the quantization noise, and you see it's somewhat separated from the spectrum of the signal. And you go one higher, second order sigma delta, and it's really separated. So this is the kind of the visual explanation of noise shaping. All right, so how does this get used in this? Well, first of all, in the standard conventional A to D, the reconstruction is done by low-pass filtering, but in a sense, it doesn't have to be in that particular form, because as we discussed, when you're oversampling in this redundant setting, there's no single dual. There's a huge, the space of dual frames is quite large dimensional. So how can we utilize this? So let's just discuss a class of noise shaping methods where we replace the difference operator for sigma delta by a more general operator H. So I'm going to set up a difference or a matrix equation in general. Y minus Q, the quantization error, is H times U. Okay, what is H? H is going to be some causal invertible operator. For us, it's going to be a matrix that is lower triangular with ones on the diagonal. Okay, so the idea is to be able to set for each given measurement vector Y to find Q such that this equation is satisfied where U is small, it's well controlled in some norm. So if you can do this, let's see what we can do then. X minus X hat, the reconstruction, is F times Y minus Q. That makes F times H times U. So if you can keep the norm of F times H small, while F being a dual of E, then you can bound the reconstruction error. And actually, if you minimize the operator norm of F times H subject to this constraint, you can solve this explicitly, and that's given by H inverse times E, take its pseudo inverse, and then multiply by H inverse. So which is what we call the H dual. Given an H is your noise shaping operator. This is the H dual of your frame. If H is a discrete differentiator, then we call F a Sobolev dual. And if it is rth order, we call it rth order Sobolev dual. So what do Sobolev duals look like? Well, here's an example. So let me see if I can point at this. Is the pointer visible? Oops. You see a random frame on the top right, okay? So it has absolutely no structure. And the red curve is a first order Sobolev dual. It's a smooth path. And the blue curve, so this is in R2, by the way. We have about 15 or so, maybe 20 vectors. The blue curve is a second order Sobolev dual. Well, the Sobolev duals follow a smooth frame path because they have to, when you multiply, when you differentiate them, they have to give you a small norm, right? So even though the original frame has no structure, it's random, these alternate duals have large amount of structure, and that actually produces something quite good. So let me just tell you what kind of results you get. So The error bound, as it can be easily checked, is controlled by the minimum singular value of h inverse times e. You want that to be large because it's in the denominator. And you also need, as I said, the state sequence U to be kind of well controlled, but that's a separate problem that can be handled by existing methods, so I will not go into that. So this is going to be mostly about frame theoretic notions. And how does one kind of control the minimum singular value of h inverse times e? H is some kind of design parameter. It's a noise shaping operator. You want to kind of design it as good as you can to make this least singular value as large as possible. And each frame and a noise shaping operator gives you a new problem. And the thing is that to estimate this small least singular value, you don't want to use the product bound because the h inverse always has a small singular value. So that will not help. In fact, you want this product to have a large singular value, and that actually does happen. So while it's kind of difficult to do this on a case-by-case basis, if you have random matrices, random frames, then there are you resort to analytical tools and you can say something quite good. And this is also crucial for compressed sensing. So this is the result that we had about 3 years ago for the Sobolev duals. Just in a nutshell, what it says is that if you use the Sobolev duals I described, it's Rth order Sobolev dual for a random Gaussian frame, then this least singular value is shown to be larger than what it would be if there was no noise shaping by a factor of lambda, which is lambda is the oversampling ratio, to the power roughly r. So you gain and this happens with high probability, right? And so this gain is consistent with what you get in the kind of the classical context of oversampled A to D. And then in that context, one also optimizes over the order R and can show exponential. But here it doesn't actually follow. You only get root exponential because there's the dependence on the order is worse. And this is the part that kind of was not satisfactory to us, that one couldn't get exponentially small reconstruction error in this context. And I will now report on the recent developments. This is thesis work of Evan Chu from Courant, and just about some alternative choices for H. We're going to now discuss some other noise shaping operators. So the motivation here is that if you do some kind of radix representation, you would get exponential accuracy in it, meaning like a binary expansion, ternary, any kind of or beta expansion. So they also actually belong to some kind of noise shaping framework. I'll motivate this with a one-dimensional example. Suppose you just have a scalar and your measurement operator is just a repetition. You just repeat the number m times. That's E. This is a column of ones. And now here's a dual or an approximate dual, which is a sequence of inverse dyadic powers of 2. Okay, so F times E is roughly identity. So you could actually use these measurements and pass them through a difference equation, which now is very similar to a binary expansion, but except you're constantly, at every kind of iteration, you're feeding the same number instead of using it as an initial condition, right? And with this, you can actually get, for that scalar you're encoding, exponential accuracy. Now, to be able to do this in the way I set it up, I have to use a quantization alphabet which has 3 elements in it. So it's not optimal in terms of its exact error performance, but it's just to illustrate this point. So it can also be generalized to an arbitrary measurement operator, again for scalars. So I'm not going to go through the details, but you can kind of normalize things, adjust coefficients appropriately, and get the same result, even if you just repeat with the same coefficient, but repeat with different coefficients. So it works in one dimension, no problem. And what about higher dimensional? This is what you want to be able to do something like this in k dimensions. And this brought us to the notion of what we call a beta dual of a frame. So for this, we gonna work with any kind of beta which is bigger than 1. It could be integer, it could be non-integer. And there will be a small matrix, as you see, ones on the diagonal, minus beta just below. And this matrix has p minus 1 macroscopic singular values around beta, and a single microscopic singular value, which is exponentially small in the size of this matrix. So this would be what one would try to use, but it actually doesn't work in k dimensions, and we didn't use it. And now Evan had the kind of very natural and clever idea of repeating this block and allowing for the dimensionality to be higher than. So here, what's happening is that there's a little bit of oversampling that one needs. So we'll repeat this little block L times. L will be bigger than or equal to k. And now this will give us a new noise shaping operator, big H. Okay? And now this big H repeats the singular values of the small h, and the inverse, of course, has the same structure. And now what happens that the capital H inverse has L large singular values that are exponentially large in the oversampling ratio if L is near k. So now with this, Evan was able to show that the minimum singular value is exponentially large in M over L. And there's a kind of a coefficient here which is related to what is much smaller frame, a frame in RK of size L, which is a condensed version of the original frame. Now I'll show a picture later on what this is, but the condensed version basically, if you partition your frame into L groups, and within each group you extract a single representative vector, and you still get a frame, and that frame controls the coefficient of that exponentially large singular value, pretty much. And then you can analyze the performance of these for Gaussian frames, and it turns out that the minimum singular value of this matrix is exponentially large in M over 2k. If you choose L economically, and this with high probability, leading to an overall quantization error that decays exponentially in the oversampling ratio. So this is up to the value of that constant. This is optimal. And it actually turns out to be that this computation of this alternate dual is numerically very stable. And the reason for that is one can instead compute an exponentially close approximation of this dual, not in the original M dimensions, but in a subdimension. And I will just show a picture. I think that will be the end. So here is what they look like, and it will make a lot more sense. So here's I have a picture of, I have 24th roots of unity on the left, and on the right I have a beta dual, and you see that I've chosen L equals 4 in 2 dimensions. So so if you just look at the 4 directions, you would have a tight frame, but then those vectors are repeated at dyadic scales. This is what turns out to be the beta dual for this choice of parameter. So this dual would give you a perfectly nice grid, and that's why you get exponential accuracy. Now here's a random frame, and on the right you see again something that gives you all the dyadic scales. Now the directions are slightly different, but it's not too bad. It's not maybe tight, but it's not too far away from it. And now it's also again roots of unity, but they're ordered in randomly. So then the directions change, but again the same vectors show up as the beta duals. So I think I will stop here, and I won't talk about the consequences for compressive sampling, but for those of you who may have seen how the Sobolev duals are used in compressive sensing, the same thing can be done here. So, so the quantization error bounds for compressing sensing can be improved significantly compared to what is available. So if anybody's interested, I'm happy to talk more about it.